Any questions besides Kelly's?
Okay.
Ethan,
In the centrifugal force lab,
right?
whenever we're finding the tension on the string, since the string is connected, would the tension on the swinging mass be the same as the tension on the hanging mass?
Yes, that is the assumption we are making. Oh, that was easy. Other questions? Because that's right, we're over there. Today is the 16th. Yes, that's right. That's tomorrow. Well, I'll set up the problem because I think she's almost done. And I think I know what her question is. Let's just take a look at box on ramp. All right. So let's take a look at a box on ramp problem. This is sort of a throwback to, I guess, material for the test tomorrow. And we're just going to start out with the initial velocity is 0. Initial speed. So, if the box is going to slide, which way is it going to slide?
Yeah.
Okay. So, let's just go through the steps here. Force diagram. Force is acting on it.
Weight, acting down.
Normal force acting up and to the right. Friction acting
Up the
up, yeah.
All right. Now, I don't know if it's static friction or kinetic friction to start with. So the force diagram, acceleration we've already established is down the ramp. Coordinate axes, therefore, I'm going to establish those as my positive directions. I hat, J hat. Decomposition, so what am I going to break up?
weight.
All right. So down the ramp is going to be W sine of theta. Into the ramp, W cosine of theta. And then normal force and friction. So those are basically the four forces, or the four parts. Equations of motion. First off, how many equations of motion will there be?
2.
All right, and what are they?
I have to take it.
W cosine theta.
You did say cosine?
Oh wait. Y minus W cosine theta equals 0.
All right, one down.
W sine theta minus friction is equal to mA.
All right, so whether it's static or kinetic friction, none of this is changed. The next thing that we do is where we bring in whether it's static or kinetic. Now, if we plug in kinetic friction, we could very easily make it look like the thing's sliding down the ramp when it's not, because we have to overcome the static before it will start to move. Now, I made the numbers up on the spot. I don't know what's going to happen. But the first thing you do is we have to establish, does it move or not? So we are going to assume maximum static. My acceleration is down the ramp, because I know physically if I put a box on the ramp, it's not gonna suddenly go up the ramp. So if I assume maximum static, that means if I get an acceleration of 0 or a negative number, it's actually not moving. Because if I get a negative acceleration, that means I have a box sitting on the ramp like this, I said down was positive. Negative acceleration means I have this thing starting at rest and suddenly the thing goes boom, which I know physically cannot happen. And so we're going to assume maximum static for the substitution phase. So I know y equals mg cosine theta, mg sine theta, minus, well, maximum static, USF, that is wrong, thank you, USY is equal to MA. And now we're solving. I know theta, I know, mass will end up canceling out. I know G, once I assign a planet. That's supposed to be the word Earth. So it's a matter of solving. So I'm just gonna take my value for y here and plop it in for y. Now, I did not give you a mass because the mass ultimately does not matter as long as it's not 0. If you are uncomfortable with that and I don't give you the mass, either if I don't give you the mass, either the mass does not matter or I made a mistake. If you come up during a test and ask, what's the mass? If I respond, and then I give you a number, that means you probably don't need it. If I go, oh, I probably made a mistake. Now sometimes I'll do the first one and then realize later that I have made a mistake, but you know, just, you can gauge it from my reaction. So I have mg sine theta minus mu s mg cosine theta equals ma. Now I have 3 terms. Each term has mass as a factor. So I'm left with acceleration is g sine theta minus us g cosine theta. And now it's plug and chug. 9.8 times the sine of 37 degrees, which is about 0.6, minus 0.5 times 9.8 times 0.8. Cosine of 37 degrees is about 0.8. I should have picked Earth too. So that's roughly 6, just shy of 6. 6 times 8 is 48, so 5.88 minus 3.94. 1.98, so one of these numbers is wrong. Plus 2.6.
3.91.
3.91.
And
No, wait.
5 point, if you round it, it'll be 5.90.
The numbers are basically right there. Give or take. All right. So we end up with a positive acceleration. Is that the acceleration of the mass? Because this assumed we were dealing with static, but we've established that we are going to overcome the static, therefore it's actually kinetic. And the advantage of not plugging in numbers at the very beginning is I don't have to make as many changes. So once I realize that it is going to move, well, that's kinetic, that's kinetic, that's kinetic, and that 0.5 becomes 0.4.
2.77. I meant the final number.
Oh. that's the acceleration. If I upped the acceleration, or sorry, up the static coefficient. Questions on this before I change the problem, using the magic of the board?
No.
It looks like to cross it out, that's supposed to be an 8. So let's make that 0.8. Still the same problem that we had before, except we're going back to the subscript S there. Hopefully 0.8 is enough. So S, 0.8. Okay, that should work.
Negative 0.36.
Negative 0.36. Once we establish that we have a negative there, we know it's physically, see, that's the math part. Now we're bringing physics back into it. If that were the acceleration, that means I put it on the ramp, it starts at rest, and it accelerates up the ramp, which we know is not going to happen. Therefore, what is the acceleration?
0, 0.
Yeah. So in this case, with that there, the acceleration is equal to 0 meters per second squared. What is the friction force? No. That is not the friction force. I assume you did 6.28, but 0.8 times 9.8 times 0.8. That's the maximum static. What is the actual friction force? If acceleration is 0, we'll plug 0 in. We can plug 0 in here. It's all for friction. No, friction's not 0. I think I saw a couple light bulbs go off.
We don't have math.
What is it?
We don't have math. Oh, wait.
Oh.
The mass cancels out.
You are correct. We do not have mass. We would need that. I apologize. Oh, get the right reaction there. Let's give it a mass of something clever like 10 kilograms.
Does that mean our friction force is equal to W sine theta, right?
Yes.
Alright, I got 47.18. This is 10 foot, wait. Idiot.
That doesn't feel right.
It's because it's not.
What equation are we using?
All right, once we establish acceleration is 0, the concept is I've got these two forces battling it out up and down the ramp. I have W sine theta down the ramp and I have friction up the ramp. If acceleration is 0, then those forces must be balanced. And so what we're in essence saying is that the friction force must be equal to W sine theta.
58.98.
58.98. So that 62 or whatever it would have been, that's the maximum static, but we never got there. Because again, the static friction and the applied force will match each other until you hit that breaking point, at which point the friction drops off. So if this is my maximum static, the static is gonna match what it needs to as long as it's not moving, and it only gets that far. It never quite gets to the very top.
What calculations did I do to get that number?
Say it again,
What calculations did I do to get that number?
to get this number?
Yeah.
Since acceleration is 0, we established that when we got the negative acceleration, that meant it's not actually going to move. I went back to here, I know that mg sine theta minus that friction force, which I now know is static, is equal to 0. So therefore, the static friction must be equal to mg sine theta. Because friction is opposing just that part of the weight.
Just thinking. I
Okay.
think it's
Nathan?
So if I plugged in, like W cosine theta for remote force times static friction, that would be the maximum static.
Yes.
Wait, can you say that again? What did you say?
Nathan?
Oh, I said that if you plug in mg cosine theta for the remote force times the static friction, that's the maximum static.
Yeah, so Fs max is mu s times y, which in this case is mu s times mg cosine theta. That's the maximum static.
I know you said this before, but, if the angle is less than 45 degrees, then the sine, W sine theta.
You're mixing a couple things there. Hopefully I didn't misspeak before. Down the ramp is always gonna be sine. It's the way it's, if I give you the horizontal, the angle against the horizontal, down the ramp's gonna be W sine theta, regardless of what theta is. It's a question of, if I'm under 45 degrees, then the larger one is going to be into the ramp, and the smaller one is, yeah. Because I've got the two components here. If I'm under 45 degrees, this will be the larger number. So if you get into a panic and going, I don't know which one's which, if I'm under 45 degrees, this is gonna be the larger value.
So sine always goes down.
That sign is always down the ramp. All right, so this started with the question that you had asked, Kelly, and this isn't exactly the same problem that you pointed to in the office, but does this at least answer some of your questions?
Mm-hmm.
Okay.
Would you further ask us for the, is this a problem that you would ask us for the max static friction?
I could. It's fair game for me to ask what the maximum static friction is.
I'm just trying to like gauge what you would ask, like how to know what we're doing in the problem. You know?
If ultimately I wanted to know what is the acceleration, I mean, there are a lot of other questions I could ask, which hopefully would lead you to that. So knowing what the maximum static is something that you would need to know, because the first time we ran, that's what this is. This is the maximum static divided by the mass. The fact that it's not accelerating tells us, well, we never exceeded the maximum static.
So if you could just do that little section times the mass,
That little section times the mass would be the maximum static.
oh, that makes sense, because that's the equation, okay.
Would you like to see a more difficult friction problem? Yeah, and a nod yes, and a couple other people who were, I'm not quite sure if just sort of bobbing
Yes.
or saying yes. I ever gave this on a 151 test, but I don't know, I think I did. I've done it on a 251 test. And just for ease, let's make this Earth 2. In other words, G is 10 meters per second squared. If, gotta give some numbers here. Use of S, why don't we make that 0.4? Mu sub K, let's make that 0.3. We'll have 4 kilogram mass. Oh, this was on the Who Killed Kenny test. 4 kilogram mass slides up the wall in kinetic equilibrium. What is the angle? All right. Let's take this apart. What do I mean by kinetic equilibrium?
Acceleration of 0.
All right, that's the equilibrium part. What's the kinetic?
Constant velocity.
Okay, we can be more specific than that. So equilibrium, acceleration is 0, total force is 0, or velocity is constant, or changing